Good afternoon. We continue with our series of lectures on control charts. We looked at the X bar chart and the R chart. These are the charts that are utilized for variables control. When the quality characteristic can be measured on a scale and it's a variable quantity, you would like to have accuracy and precision in place, and therefore you'd like to utilize the X bar chart and the R chart. Now, there are obviously other quality characteristics. For example, the goodness of the fit of the cap and the body as an example, and a number of other things. For example, this bottle of water may not be transparent, may have beyond the permitted degree of pesticides or biomaterial, stuff like that, which you'd like to avoid. So you'd then probably call this product either acceptable or not acceptable. You do it on a go no go basis. You do your quality assurance on a go no go basis. How do we monitor? How do you monitor the production of such things? How do you assure quality there? The same thing could apply for service situations also. When we have many instances that cannot be measured, many instances of attributes that cannot be measured, but they are attributes. They are like either good or bad. For such things, there are other charts, and I'm going to be giving a couple of examples. One is the P chart. The P chart calculates percent defectives in a sample. So, if I collect a sample of, let's say, 100 items, how many defective items are there? I could start monitoring just that, and I would do that. I'll calculate the quantity P, which is the fraction defective in that sample, and then start producing a chart on that and find out if that variation is within the acceptable range or has it gone beyond that. I could do the same thing for the number of defective items in the sample. So, either I could do fraction defective monitoring, or I could do number of defectives found. Both of those could be done, and the charts are different. The first is the P chart and the C chart, and I'll show you the limits for these also. So, in fact, what are we talking about? We are talking about quality characteristics that could be measured, not that cannot be measured, but can be judged on a good-bad basis, pass or fail basis. When data consists of characteristics like this, we would utilize the P chart. And now you are familiar with the control limit calculations, and control limits are those extreme values that are reached very rarely. And one such thing is for the P chart, for example, the upper control limit is going to be P, which is the historical average, plus Z times sigma P. The Z value here is found in such a way that the probability of exceeding this quantity, this upper control limit, is going to be very, very small. Is going to be like going beyond the 3 sigma limit on the X bar chart. And the same thing we do on the lower side also. So, we've got a lower control limit on the P chart, and that will be done as P minus Z times sigma P. How do I find this Z again? This Z value is from the standard normal table, and it gives you the cutoff point, the value of Z beyond which only a small tail of the normal distribution lies. And these of course have the assumption that the normal distribution is applicable in this particular case, which is like the distribution of defectives, for example, fraction defectives. It's very easy to figure out the standard deviation of this, and because the standard deviation of defectives, that thing is controlled by the binomial distribution. Binomial distribution is a pretty good model for it, and if that is so, then we can find the sigma as sigma P is equal to P times square root P times 1 minus P divided by N. This is the sigma limit for P, and this same sigma limit I can plug in there. This same sigma value I can plug in there. I can find the exceptional limits on the P chart. I can find the upper control limit on P chart and the lower control limit on P chart. In some cases, when the lower control limit, because there is a negative value there, it's possible this quantity may turn out to be negative. And of course, defects can't be negative, so we make this equal to 0. This quantity is negative, the convention is make it equal to 0. So, in fact, we are still using the normal distribution as to try to locate the points that are like the extreme situations when the process is under normal control, under statistical control, and that we do just by again plotting the chart in such a way that we got these upper and lower control limits at 3 sigma P this time on the high side and also on the low side around the average. Here's an example. Sample number 1, there were 20 samples collected, each had 100 pairs, and these were genes. They were inspected, these genes were produced, they were fabricated, and they were inspected to see stitching defects or buttonholes not being right and so on and so forth, or some blemish on the cloth, or some seam not being proper and so on and so forth. So they were looked at that, and a number of defective genes in the lots of 100 each, they were found, and those numbers are shown in the middle column here. So 6 defectives in the first sample of 100 genes, none in the second, 4 in the third, and so on. And there are 18 defective items in the 20th, so that's like this. And proportion defective would then be, of course, 6 divided by 100. That's the size of the lot. So I've got that thing there. These are my p-values. I'll have to put control limits around these. So for that, I just go to the control limit formula. And the value of z, this time I'm going to be taking a 3 sigma limit. So I put down 3 there. And this is the value of sigma p. And I've got that quantity put down there. And if you do the calculation, you'll find that the upper limit turns out to be 0.190 and lower limit turns out to be 0.010, which really says if the value of p, p is the fraction defective in any of those lots of size of 100. If it's above the control limit or if it's below the control limit, it's an exceptional situation. I have to stop the process, investigate the causes for it, just like we used the reaction plan in the x bar r case, and I did that. Well, when this was done, you had a suspicion that perhaps 18 defects were too many, right? When you looked at the 20th sample. And see what they found? They plotted the p chart with the upper and lower control limits shown as calculated. And after plotting the chart, they did find that in this zone, the chart went beyond the control limit. So this is like an opportunity for finding the defect there, finding the issues there, the problems there. When this is done, every time the like in the X bar chart or the R chart, the moment the chart goes beyond control limit, stop the process, take a look at it, and come back and see if indeed everything is okay, or yes, something did fall out, go beyond the set limit, for example, and then you'd restore the process to its normal state of affairs. Another example there, again, there's n. N is the sample size, which is like how many items are there. We had 100 genes, and here we've got something else, and there are 50 of those. How many defectives were found? Then I find my p value. How is this p found? It's 2 divided by 50, or 4 divided by 50, that will give me 0.08, and so on and so forth. So these quantities are found by looking at the number of defects divided by the sample size. That's what gives me this. I do an overall, and I find from this the overall, like we had the x double bar. In this case, we'll have p bar, and this p bar would be utilized then in calculating the control limits, and those are done here. Look here, the p bar turns out to be this, and I use my control limit calculation. I find my sigma p, 3 sigma p then, and I find my upper control limit, which is 0.123, and lower control limit turns out to be 0 because it turned out to be negative, so I made it 0. And then lo and behold, I've got my little control chart there. Everything is in control because the upper control limit is way out there somewhere. And again, another set of data there. I could do the same calculations, absolutely no problem there. And I check out the sample size, divide that by the number of defectives found there, and I draw my control chart there. So they show the calculations there, and they show the example of the control chart. These are quite easy. Another way quality characteristics could be measured is the C chart. The C chart it's looking at the number of occurrences of defects per unit. So it could be like, for example, if it is, I don't want to have a defective calculator, but say if I had sticky keys, or if I had the protective thing here with some scratch on it, or the case, the cover did not fit very well. The case was there, but when I tried to put it back together again, it did not fit very well. That would be a defect. So there could be multiple defects on one item there, on one item there. If there are multiple possibilities of an item there, what I do is I construct this C chart, and the C chart is found. It's also a count, It again has its own control limits, and I'll show you the formulas for it. And some examples are scratches, chips, dents, or errors per item, or cracks or faults per unit of distance. This could be true, for example, for cables and stuff like that. Or breaks or tears per unit of area, like for example, if I'm looking at a piece of cloth, for example, a curtain or something like that, I might take a look at number of defects found per unit area. Or pollutants per unit volume of liquid that you find in a puddle or in a lake or somewhere there, or in a well, oil well, for example. Or calls, complaints and failures per unit of time, per hour, how many calls are not being answered properly, for example, or they are dropping off because the queue is too long or stuff like that. Those things can be monitored as defects per unit. So the unit you set in a manner that makes sense to you, find the number of defects you produce, and the rest of it is very similar. I will just remind you of one thing there. We are using the 3 sigma limit. In the case of x bar, we were able to comfortably use the normal distribution because the central limit theorem told us if we use the average approximates the a standard normal variable, and therefore there is no real issue there. You could use the 3 sigma limit there. We kind of did the same approximation we did when we did the P chart. For a defect, when you're counting defects, for example, with the C chart, when you're counting defects, defects actually have a distribution that is Poisson. And the Poisson distribution is such that the mean is lambda and the variance is also lambda. So imagine that I used C to take care of this. C is the C bar, for example, the average. C bar would also be the estimate of this. So therefore, when I'm trying to draw my 3 sigma limits, the upper control limit will be, I'll have obviously C hat, C bar, plus 3 sigma x. And what is sigma? Sigma is square root of this. In fact, this leads to sigma equal to square root of C bar. So I use here square root C bar. And lower control limit is going to be C hat minus 3 sigma, and that is going to be this way, C bar. So these are dependent on the Poisson distribution. But these are still the extreme ranges. They are still the extreme ranges. I estimated my sigma using the Poisson assumption, so I was able to do this jazz. But in actual fact, these still turn out to be limits. In fact, they are probability limits. They are exceptional limits. To exceed them, the chance of exceeding these limits is very, very small. It's 1 or 2 or 3 parts per thousand or something like that. It's a rather rare occasion. If it's a rare occasion, there's a very high chance that an assignable cause has disturbed your process. Therefore, the moment the C chart goes beyond your control limits, for example, we'll take a look at one example there. There is a C chart, everything is staying within control limits. No problem there. No problem there. And to get there, of course, we did all those calculations. We looked at the formulas. We looked at the raw data. We found the overall grand average, which is like, I'll be 39 divided by the total number of items there. Here in this case, for example, it's an interesting application of the C chart. Hotel suite inspection. This is a service application. Defects we found per room. Stationery was missing. Curtain was not pulled to complete close, for example. The bed sheet was slightly ruffled, and the ashtray was slightly nudged to one side, and so on. But these are things that the guest may not like. So these are all marked as defects. I did that, and I constructed my sum of C, and I divide that guy by the number of items there, and I end up with my quantity there. And I use my control limit calculations, and I end up with 39 divided by 26. 26 items were used. So C bar is there. Upper and lower control limits have been set. Lower control limit had to be trimmed at 0, like our P chart. When it became negative, we made it 0. But I've got now my control limit there, and this chart, as is shown here, shows everything is A-OK. I need not really worry too much about this. I could have another example. There are 2-3 examples there. There is one about bank complaints. Complaints are piled up over 14 days, and then of course I've got 42 as the total number of complaints there, and I could do the same thing there. It's not very difficult to do. So again, I could construct the C chart there. Now let's take a look at what sort of things we've been using. For the X bar and R chart, we use the normal distribution to find the control limits. For the P chart, we use the binomial distribution as an approximation to normal distribution. It became approximated into a normal distribution. And then for the C chart, these were counts of defects. We use the Poisson distribution. Which chart to use when? That's also a question. How do I do that? I start with the quality characteristic. What is it that I'm concerned about? Is it a variable characteristic like dimensions, for example, dimension of these things that I can measure on a scale? That will be like one class of quality characteristic. The other is good or bad. So the caps fit or they don't fit, good or bad. The assembly is okay or the assembly is not okay. So that will be an attribute. Variables chart, I ask the question, is my sample size greater than 1? If my sample size is not greater than 1, I just use a plain X chart, the raw chart, and a moving range chart. And I use the same principle that I use for my X bar R chart. But the chart I'll be using here is X bar, which will X chart, which will give me an indication of the accuracy of the process, and the moving range chart will give me an idea of the variation of the process. If n is greater than 1, that means the samples that I collect, they have a size that is greater than 1, like 3, 4, 5, 6. What I would do is I'd construct the X bar chart and R chart. If my sample size stays the same, it's very easy for me to do the calculation. And if they don't stay the same, I might use a computer, I might be able to do it. Either this. So I could be using the X bar chart and the S chart together, or I could be using the X bar chart and the range chart together. This is the story for your variables quality assurance. Online quality assurance using variables approach, variables measurement approach. For attributes, if it is defectives, you go to the P chart or the NP chart. N is your sample size. And in that case, I could probably do this without much trouble at all. Something that is important for the P chart is your sample size need not be the same, because the control limit itself has n built in there. So in fact, if you go back to the formula that has the P chart there, the P chart will show you that sample to sample there may be a change in sample size, and you will have no problem at all. Use them as if the charts are like the old 3 sigma up and down type of control chart. No issues there. If you're counting defects like you do in a hotel room, for example, if the sampling unit is constant, that means no real issue there. You could just be doing, the defects per unit. So if I'm just looking at one room each, there is no problem there at all. So I do that. But suppose I'm inspecting these calculators, and I've got, sometimes I get 3, sometimes I get 5, sometimes I get 1, and so on and so forth. I should be using what is called the U chart, which is like, in that sample, how many defects did I find? In that sample of size 3 or 5 or 2 or 0, not 0 of course, 1, how many defectives did I find? How many defects did I find? Once I know that, I'd be able to use the U chart. And the U chart runs very, very similarly to the C chart there. Design issues, what are some of the design issues there? Subgroup size is a big issue. Subgroup size is your sample size. It turns out that this is what determines the sensitivity of the chart or the power of the chart. The larger is your sample size, the quicker you are to detect a shift in the process. So if your average is, let's say you were drawing the X bar R chart, and in doing that, suppose it turned out that you had a choice of sample sizes. Something you got to remember is, when you collect a sample, you are sampling these bottles, bottles of water. How many should you collect and when should you collect them? How many should you collect would depend on the power that you want in the chart. What is this power? The power will tell you if the fill quantity varies even a little bit, I should have large N. If I have large N, the chart will have more power. It will be able to talk about slight variations, even slight variations in fill quantity. That's one consideration. The other consideration is, if I do expand my sample size, it's very possible that the different bottles that I pick up, those might be produced under different conditions. If I collect, for example, 20 bottles, the first 5 or 6 might be produced with one speed of filling. The later ones might be with some slightly different speed of filling because hydraulic pressure changes, something else changes, some controls change and so on and so forth. So in fact, it turns out that one of the requirements we have in statistical process control is when I draw a sample from production, these should reflect one condition of production. That means they should be alike. Yes, there will be statistical variation, but it's not that these were collected when voltage, which is an input to the machine, fluctuated from 110 volts to 120 volts to again came back to 97 and so on. If that happened within the collection of this sample there, I will be looking at a mixture of the influence of assignable causes and random causes both. In fact, within the sample, the variation should be mostly chance causes only. And sample to sample variation, which is like one sample here, another sample here. If I'm comparing the difference between the measurements there, the average measurement there and the average measurement in this one, these two should reflect the impact of assignable causes. So let me repeat this again. The variation that I would like to see within a sample should be of the homogeneous kind. Each of these items should have been produced under comparable conditions. This is called variability within the sample. And when I collect a sample at some other point in time after maybe 1 hour, the difference between the measurements for this one or the statistics for this one and this one, that should reflect the impact of the assignable causes. And those may or may not have changed from going from here to there, from here to there. If this does not happen, I'll not be able to really catch the presence or the disappearance of an assignable cause. So, sample size should be determined with these considerations. Within the sample, I should be able to see the natural variation of the process. Between the samples, I should be able to see the impact of the assignable causes. Now, this might seem a little complicated to you, but if you pull up a book on statistical process control, they explain these things. There may be some economic consideration also. For example, can you live with an off-spec, a process that is not running very well? For that, you need to have the consideration of power, and for that, this power curve that I show there. These basically tell us the probability of detection of a problem is going to be higher for a small change in the process when my sample size is large. This by far, what I am discussing, is probably the most complex part of control chart theory. So if you do not understand this completely, do not worry about it, but keep your N near 4, 5, 6 and let at least a sizable production take place, which could be like after an hour or after maybe a shift or something like that, to collect the next sample. If you do that, you'll maximize the visibility of the assignable causes, and you'll make sure that the base variation, which is due to the chance causes only, that also is apparent and is pure. Within a sample, you only see what we call chance variation. So just go into this a little bit with your statistics, with your SPC book, and you'll be able to probably pick up the thing. Now there is a way to also get warnings out of the process, and those are done by pre-control. Pre-controls are done, they are also control charts just like the other ones. And pre-control charts have 3 regions: the green zone, the yellow zone, the warning zone, and the red zone. and the tolerance limits are used here in place of control limits. When I'm doing pre-control, I normally use tolerance limit, or specification limits. Those are used here. Again, a fairly decent book on statistics, statistical process control. It should be able to explain to you what the use is, what the utility is of doing your control chart. Now let's get into using Excel to prepare your control charts. Now, I have a personal bias. In fact, I'm a strong supporter. I'm a strong supporter of using Excel. And also, I get very disturbed when control charts are prepared after 7 days of data collection. I get very disturbed. If it is done almost immediately, you don't need to do a lot of calculations. You can get your chart done very quickly. I was in a factory, and this factory had a built-in SPC system. It was like Excel, but it was built into that automatic machine that was there. It produced items, and it measured the items instantly, almost instantly. They had some gauges there that produced really, really good quality measurements there. Very fine. They had good precision and everything else. That was exceptionally good. We got the data. We got the data within a minute of production. So samples could be collected also. You could push some buttons, have the samples taken out. It would do the X bar, it would do the R. It will come back and display the X bar and R. And of course, the control limits were already there. Those had been done earlier. And with that, you could figure out right away, oh, is the process in control? It is not in control. Is it drifting? Is it not drifting? Is it cycling? Any of those things could be found very easily by looking at the chart online pretty well. It was all being done instantly. That I favor a lot. If at all, if you could reduce this time of production and time of looking at the chart, if you could reduce this time, if you could make it almost coincide, if you could do that, you're doing the ideal thing. Because then there will not be a lot of production done in a situation when these things might have really, the process might have gone out of control and you continue to do production. The other extreme, which is what upsets me a lot, is engineers will go out to the plant and they'll collect a lot of data. They'll carry their laptops and they will start keying in this data. So they can't really do this when production is going on. So they'll say, guys, please send me last week's data and I'll do it in my office. So they take this last week's data and they're doing all this. So they produce this little thing and they produce a very nice looking chart, a very impressive chart. They produce this chart and the chart comes out and it's then printed out, a laser printer and everything, and it's mounted on the wall. But what is this about? It's about last week's production. And during that last week, if there are certain things that went out of control, for example, my God, when would be the opportunity to fix them? Because that data is old and that situation is gone. The production is already over. Maybe the goods are already packed. Maybe they've been shipped also. I'm trying to do online control, but in actual fact, what I'm doing is I'm delaying this whole chart preparation business just because I want to use Excel conveniently. I'm producing my chart 1 week later or 2 weeks later. And in some places, once in a quarter. What use is that? It's certainly not online control. If you want to do online control, find a way, find some way by which you could really go out there, collect the data and produce the chart quickly. What do the Japanese do? Well, the Japanese, first of all, don't have this kind of variation in their processes. But in processes that they need to measure, they have people trained so well that they can produce these charts on an online basis, pretty close to online basis. So they'll fabricate something there, they'll make some measurements and produce the chart. Let me give you one example that I saw in this country, in your country. What I found was, I visited this company called BHEL, Bharat Heavy Electricals Limited. These are people who produce huge, world-class power plants. And most of their power plants are turbines and they are generators. Those are produced by doing this. They are the people who cast huge, huge covers for these generators. And those are as big as this room, for example. Huge. They go into 2 to 500 megawatts. That's the size of the, the power production capacity they have. capability they have. Now, inside these turbines, of course, there are those turbine blades, and those blades are amazing. They are like they're like jet engine blades. That's what they are like, and no worse than them. They're just like jet engine blades. They use, because they are exposed to high temperatures, steam, pressure, a lot of stress, blah blah. All those things are there, so they must have exceptional performance. I happened to be visiting one of these BHEL factories, and the city is Hardwar, which is in the Himalayas. When you go into the mountains, it's just the beginning where the mountain begins to rise. I was there in that plant, and I gave a talk on quality assurance. Then I went down to the shop floor. I just wanted to see the action there. I'd heard a lot about BHEL and their exceptional quality assurance programs and everything else, and their level of training and all. So I went out there. I went out to the floor, and lo and behold, I found a machinist there. He was grinding these turbine blades, and the turbine blades were this long, and they were they could be held in one's hand, and he was doing the machining. A fair amount of it was done automatic, then he did some others, and so on and so forth. And he was doing this one after the other, but after every time he completed, fabricating one turbine blade, he'd take that turbine blade and he'd bring his gauge and he'd apply the gauge right there and make a lot of measurements. On certain specific spots on that turbine blade, he would make the measurements. And they would write it down. He had a table just like here. See the table there? See the table with the data there? He would just fill them out. Those he filled by hand. So each blade would have some measurements. He was doing pre-control. I looked at that and I found he was doing this totally religiously. And also I looked at his work, top notch. It did look like he had real good training in a machine shop, and must have many years of experience also. But he was not very old. He was like in his 30s, mid 30s. So he was ambitious, top performance person there. I found him spending quite a bit of time filling out this data sheet. Then he would pick up the next blade, and that blade would have the same fate: machining, measurement, machining. He did all that. Then he put that blade aside again, made the measurement data, he entered the data there. Then he went down, did his X bar calculation. Then he did his range calculation. And then, would you believe, he plotted a few points on the control chart. It was right there. So the top half was the data, bottom half was the thing, and he was doing this. Every time he took a blade out, he did this. I walked up to him and I said, sir, what do you do? What is it you are doing? He said, well, I'm, machining these turbine blades. That's my job. That's what I'm good at. And I've been assigned to do these things. Here's the design, here's the drawing, and so on and so forth. Here's the machines, and I operate these machines, and so I'm producing these turbine blades. I said, great. That's a good piece of work. By looking at your grinding, I would think this has come out of a machine, and you're doing it by hand. Really hats off to you. Great. But tell me one thing, why are you wasting your time in this measurement, that measurement, all these things you're doing? My God, what is the point in doing all these things? You're making this measurement, that measurement, and so forth. Is this really good? You're wasting so much time. You're wasting so much time in making these measurements, and it's just going on and on and on. You're doing measurements, you're entering the data. This is really a waste of time, I think. I think it's just a waste of time. It's a waste of a lot of time. Why would you rather not focus on your machining and forget about this data collection, charts, and all these things? You're good at machine, man. And why are you? He kind of, gave me a stern look. And I was a stranger. It was somewhat, I was also myself a little shaken up looking at his piercing eyes. Sir, who are you, by the way? And what are you doing here? Before that, I told him I'm a teacher. I came here for him. I again repeated that, well, I'm a teacher, and I was kind of intrigued because you are making a lot of measurements, and then you're putting them on a piece of paper here and trying to draw these charts and all. You're doing this right here. He said, sir, let me tell you something. if this one blade gets made badly, that means there are some problems with it, and that would show up only on that control chart there. I will either reject it or have it sent to a special place where they will be reworking on it. I will not probably do it because it's some other department that's in charge of looking at all the large problems there, and they are supposed to be taking care of it. My job is basically to do the first grinding and then produce this chart there. And every blade has an ID. So I know which blade has produced what kind of data. I said, but why is it important? You're producing so many blades anyhow. You probably grind 20 blades a day. So why are you doing all this writing and so on? He said, sir, let me explain this to you. If this blade turns out to be faulty, it's going to create some real havoc inside the, it will probably vibrate inside the turbine. There are a lot of pressure fluctuations and so on, and alignment or something else. If it is wrong, then perhaps the turbine is going to shut down. There are control systems that will shut down the turbine. That means the generator is going to shut down. That means the grid is not going to have supply from this particular system there. And that grid is connected to Delhi. So you might be from Delhi, you'll have no power. And how did this happen? Because that one single blade that was not machined right. And I didn't catch it when I was producing it. I said, my God, what kind of training does this person have? What level of understanding he has? It's really exceptional. I mean, to me, I had not met many machine shop people like that. So to me, it was just amazing that this man knew the value of producing data and using that as feedback right then and there. And that's the beauty of these control charts. If you use them right, they will tell you right away that the signal is there. So what charts are we looking at? The first chart is, of course, the X bar chart, the R chart. It's like the first chart you can construct very using Excel. You could also very easily construct the X bar chart and the S chart. The reason is, all the calculations are happening in the background. And you are able to focus on whatever you want to focus on, which is your analysis, which is pulling out your checklist, doing your studies and so on, doing the investigation and so on. That's what you should be doing, really. You enter the data, you make the measurements and all, that's all fine. But you should really be doing thinking instead of doing this bullwork there. So this is where Excel is great. And Excel produces some very neat graphs, very accurate graphs. That's something it's able to do. And when you plot these charts, if you do it by hand, if some mistake is there, you'll have to erase them and all, which is not a problem with Excel at all. So that's there. I can do the same thing using my X chart, individual chart, or the moving range chart. I'll have the same effect here. I'll have whatever I do with my X bar chart and the range chart, I'll have the same thing done here. No problems, no issues there at all. So I have my individual chart there and also the moving range chart. And the moving range chart will give me the signal just like I get my signal from a range chart there. No real problem there. Then I've got these attribute charts, and again I can set up an Excel sheet to be able to do this. And I do that, I key in all my data, I rig out some of the cells there with the appropriate formulas, and I got these formulas there because I know where they come from. I open the book, I plugged in the right quantities there. I refer to some cells where I've got the references, the pivots, and I'm able to get my control limits there. Once I have my control limits, I have my regular reading there. I can do my comparison quite easily. Once I do that, I can construct my P chart without any trouble at all. P chart also can come out of the Excel thing. I can again focus on troubleshooting. That I'm able to do. So P chart would really be no sweat at all if you did it this way. And this is also not very difficult at all. And notice here something that I did not show you earlier. Notice the variable width of the control limits. And can you guess why it is this way? Because the P chart, the control limits of the P chart has this N in the denominator. I will see if I could find that formula for you. At some place I've got to find that formula for you. Just bear with me a little bit. I'm just going to take you there. It's not that far. And you'll see that the limits, look here, right there. This is sigma P. and it's got that sample size right there, which means if sample size is large, for this sample, sigma is going to be small. If n is small, sigma is going to be large, and that means in one case 3 sigma limit is going to be narrow, in the other case it's going to be wider. And that's exactly what you see when you come out to the P chart that has been built using our friendly, very, very friendly Excel. You see the control limits there, and they are varying. They are varying in width because each has a different n. How do I know that? I go back to the sheet there and I see the sample size. And look at the sample sizes, 137, 158, 92 and so on. How come these are varying? Oh, these could be hourly production, and nobody really knows, nobody really can guarantee that hourly production is going to be exactly the same number of units every time. So those are different. So sample size is varying, n is varying, and if n is varying, my the control limits are going to change, and I've got this variable control limits there. They behave still the same way. The same theory applies. You forget about the history. You just look at the latest. You look at the last P point that you want to plot. Relative to that, you compare the position of that P value that you've just found to the location of its own appropriate control limits. Just see if it has exceeded its own control limit. So that would be like a very easy thing to do. This is something that again can be done quite easily. And similarly, we got the NP chart done the same way. And then we've got the C chart, which also can be done quite easily. Once you got the data there, Excel takes like a fraction of a second to be able to do that. So I'm able to construct the C chart also. C chart is there, U chart can be done the same way. And notice here the variable control limits there. That's also there. Something you got to remember when we talk about control charts. Something you got to remember, and you can't really throw this away. We are constructing the control charts to be able to get signals out of them. And signals are basically indications of major process disruptions. And this is being done online, that means as close to the actual time of production as possible, so that you can take corrective steps very, very quickly. So if you look at the old X-bar chart, you should not wait for 1 week or 2 weeks before you go out and plot your chart, because then the production, later production would be in history. It might have been packaged up, packed up and sold to people. You don't want to do that. You want to catch it as quickly as possible. If there is an exception, catch it as quickly as you can with the help of the control charts. There are certain requirements for implementation of control charts. First of all, something that is very important that I'm going to be discussing in the next session is have an audit done of process capability. And process capability is a really, really cute indication of whether your process or your machines or your factory is capable of supplying good quality product, acceptable products to customers. In fact, do you have the capability of satisfying your customer with any randomly produced part or product that you produce? Is it capable of meeting specs? That's what is done. That's what is determined by doing process capability analysis. So this process capability audit is one of the very first things that you must do. In fact, if you're going toward ISO 9000, you can't escape this today. With ISO 9000 2008, you just can't go around this process capability measurement. If you're doing a Six Sigma project, if you want to launch into DMAC, you should know where you are. If your CP or CPK, these are the process capability indices, if these are near 1 or 1.2 or 1.3, my God, you've got a long way to go. Because Six Sigma requires or is equivalent to the CPK of 2. That's an exceptional level of high quality. You've got parts per million defectives. In fact, only 2 or 3 or 4 parts in a million in a Six Sigma process are going to be beyond the control limits, are going to be defective, are going to be the ones that we call defective. Top management commitment. This goes with any kind of quality program, any kind of program in a company. If it is to succeed, it must be driven by the man up top. I don't mean God, I mean somebody who gets paid a little bit more than you. And he's the one who's got to be the champion for this. Many times process SPC, the SPC project champions, these are process owners. They have some interest. They want to make sure their shop gets in ship shape. This is something that is required by many managers. They want their process to kind of rise up. So they sometimes become champions of these things. And this could also be a six-figure project. It could be easily cast as a six-figure project. You install SPC, you install the monitoring system. SPC is a monitoring system. By itself, it does not control anything, because it requires that control loop to come back and control the causes. A production system has causes and it's got the output. Unless I control, unless I look at the output, find the reason to change or adjust the process, unless I do that, there will be no change in the process. Under SPC, we do that by looking at statistical signals out of the output, which will be done by comparing the X bar value or the R value to its control limits, its respective control limits. Once we do that, we know whether I should leave the process alone as it is, or should I take some steps to try to make sure that the process is in fact in need of some adjustment or some exceptional treatment there. Initial workable project, this is something you should start with. Don't get too ambitious. Start something small. I started a petrochemical process in Singapore in the late 70s. At that time, the first struggle was to try to tell people that, people knew plotting of data, but we were doing that with a specific purpose. We wanted to get signals of exceptional situations. Whenever there were exceptional situations, we wanted to get a signal. And for that, we had to make sure we train people, we let people know what we were doing and what our broad approach was going to be. And we took a simple process, we started monitoring its output. This was actually a pump which was misbehaving, and people didn't quite know what was happening. Was the pump itself that was the cause of the problem, or the input that was coming to this? And we found that the slurry that was coming in, that slurry was not homogeneous. And that was causing the pump to struggle at times. And that we did that by monitoring the output of the thing, and we found that we could easily find that there were occasions when there was almost no output coming out because the sludge was too thick to go through the pump. Something as simple as that, and this pump was a small unit in that large, huge chemical plant. And we had to do that with most of the equipment that was out there. And we had to make sure the controllers were doing their job. Only then, it took us 2 years to get to the point when we had a controlled process. And our production was comparable to the benchmark process, which came out of the R&D shop. So now our production after 2 years of study and SPC became more or less what our R&D chief was producing in his special pilot plant. We could do that. Employee education and training, this is very, very important. Otherwise, people will just think you're counting beans and, kind of twiddling your thumb. That's what you're doing there. You're there, but you really are not adding to production or something. So what are you doing? You're probably asking people to stop this, stop that. So they need to be trained, they need to be educated. The Japanese do this to the point when any worker can actually look at a chart, he can interpret the chart. Plotting the chart is trivial. And the bottom of it all is you must have exceptional quality measurement systems. That comes under gauge R&R. If your measurement systems are no good, the data that you'll be using to produce these charts, they are also going to be no good. So therefore, please make sure you start with some sort of gauge R&R assessment. And the industry norm is that the errors, the sigma that is with the gauge and R&R component of it, it is 1/10 of the sigma that you expect to see in the process under natural conditions. Under natural conditions, the process will have some variation. And your gauge R&R sigma has got to be 1/10 of that. If you do that, you've got a decent measurement system there. Almost no measurement system will lead to zero repeatability, zero error repeatability and zero error reproducibility. Almost never you'll find that. But you got to control the technology, the training and all those things in such a way that you end up with a measurement system that produces sigma, its own sigma, it contributes its own sigma. No more than 10% of the variation that you see in the final process there. That means what you're concerned about is then going to be 90% or more due to the process itself. That's going to be very, very important. So let's summarize what we've done so far in these last 3 lectures that span various control charts. We looked at, we appreciated, we ended up seeing various examples and so on. And we understood that statistical process control provides a simple yet powerful method for managing processes while avoiding process tampering, that means adjusting every little thing every 2 minutes. If you find a new driver on the road, that fellow will try to adjust the steering wheel every 2 seconds. Every 2 meters he is going to be adjusting his steering wheel. That's not an experienced person. The experienced person has a SPC built in his head. He's also got control limits in there. He may not be able to spell out exactly what it is, but he will be able to tell you, it's only under these conditions I will touch or I'll give a turn to the steering wheel, otherwise I'll just hold it steady. Your process should run like that, like an experienced driver. A process in control is ripe for the next stage, which is like breakthrough improvement, which is what you'll be doing when you go to Six Sigma. You need to have these breakthrough improvements. And for that, the tool is obviously, SPC is not enough. SPC will do the monitoring for you. It will set up the candidates, it will set up the occasions for you to come in and intervene and do your troubleshooting and so on, remove the assignable causes. But what you need there is more powerful method, one of which is design of experiments. And we'll be studying some of these things. We'll be looking at some of these things. And of course, a process will always have some chance variation. It's not true that you do all these things and you remove every kind of variation from the process. That's not true. In fact, if it turns out that the variation that you have left after you removed all the assignable causes, all the vibrations, all the tool breakage, all the poor training and so on, even after you've removed all those things, there still are going to be some sources of variation. And those are going to be too expensive to kind of control in the plant itself. For that, you need like a technological jump, which is like finding justification for going towards Six Sigma. As an example, if you are trying to reduce the natural variation of the process, you got to go up on technology. That's very important, and that must be justified economically. It probably should, consider getting into, for example, if you're producing bearings, as an example, bearings are used in our roller skates. Bearings are used in, various types of appliances. Bearings are also used in automotive. Bearings are used in, for example, axles of two-wheelers, for example. And bearings are also used in aerospace applications. And these are all different types of bearings. The ones in roller skating can tolerate a lot of variation. The parts don't really have to fit in exactly. The clearance within a bearing does not really have to be that precise if the application is only rolling around town, for example, roller skating around town. When it comes to two-wheelers, motorcycles, for example, it's got to be a little better, and these are rated by the bearings industry. And then, of course, if you're trying to reach even higher, you're going to machine tools, your bearings have to be even better. And the ultimate is the same, the bearing that will look about the same. It may cost 50 cents for a roller skate. It may cost $2,000 for an aerospace application. And they would look just about the same, but the difference is in the capability of the machines that have done it, the precision with which the process was controlled to deliver the final product, and of course, the durability and the rest of it. Because parts that are defective, they are not going to last a long time either, because they don't fit very well. They kind of rub onto each other and they create trouble for each other to coexist. I really appreciate this chance to be able to talk to you about control charts. We have many other tools that I'll be bringing out one after the other. And of course, one of the big one is going to be our design of experiments, which I'll be doing in some short time with you. Thank you very much.